um, and good morning to everybody. So I hope you enjoyed the night and maybe the evening. Um, and get some kind of, let's say, discussion about yesterday's talks and discussions. So today I will start with a presentation about in the end, about our products in the chassis development, so as some examples of the steering and brake control systems, with a little bit on the focus on NVH and comfort aspects. So let's give a start. So as said, in that F, for the company I'm working for, we have a lot of different products for sure. We have as well our e-mobility section or department, but I'm from the chassis department, so focusing on dampers, steering system, braking, but as well we have there a lot of e-motors in it, or let's say small actuators, which are not that big, but as well electrical driven motors. And here's just a portfolio from that F, where we have our let's say electrical motors in, and as said, if I find a laser, here this is the main focus on the chassis department. So as said, we have the steering system, we have braking systems, chassis components like damper and stabilization systems, and for sure then the other products with the e-drive in the commercial cars as well, and as well some let's say in industrial products or in bicycles and so on. Overall, what we try and do, we have some kind of competence center where we combine all these activities regarding our electrical drives or electrical motor, and for sure we try to increase our efficiency and using some kind of reuse in different products, and have some kind of modularization. For sure that's somehow limited, if we're talking about very small actuator motors, they are different or very different to e-machines for the drivetrain for sure, but at least within the chassis department we have let's say different we have some kind of base models which we then combine and use this in different products. So we have a steering motor which is used in front steering, rear steering, as well braking motors for the actuator are somewhat double used. Another aspect, as said here, is from the ZF chassis development, so we call it chassis 2.0. The main point is that we have everything in one single, or in our hands, which is relevant for the chassis. So we have the steering system in front and rear, we have the braking system, and we have the damper system. So if you drive a car beside the drivetrain for sure, which is the, let's say, the engine and the heart of a vehicle for sure, everything else which is on the chassis, so which is, let's say, the base or the foundation of a vehicle, is in one hand, and with that we can develop some very unique and exciting vehicle motion techniques. So therefore, as well, we are focusing some kind of vehicle or central vehicle motion architecture. We have our own platform where we integrate all the controllers, and with that, we can combine the architecture with our software to get these kind of or unique driver experience, because we can then really choose which actuators are combined or are used in combination with other actuators. So for instance, as I think yesterday there was a talk about using the braking system as well as a steering gear, and as well vice versa. There are some kind of interactions you can use to have a very, let's say, specific driver feeling, and as well as some adjustable driver feeling. So you can really choose between comfortable driving over very rough surfaces, but as well as sportive driving, a very direct driving, by choosing the right components and control of them. So with this, so say if we control the whole chassis components like brakes, steering, shock absorbers, then, as said, you can have a very, that you can really handle the vehicle more or or much better than if you just control the individual software, maybe with some inputs from the braking system. So typically, if you have a controller, there are some data on the CAN bus or FlexRay bus, so you know, okay, now my vehicle is steering, then the other actuators recognizes and can adapt their control strategy, but it's more like an acting on behaviors and not a combined combination in the control strategy, and that's what we as well focusing in. So what's then the, let's say, some benefits marked here? So you can have a sportive driving with different feedbacks, but as well you can have this kind of decoupled or really smooth driving about rough surfaces, and as well for a company as ZF, it's let's say interesting aspect is that we can as well sell our software as a product. Nevertheless, that are some benefits, but in the development chain, we have to focus as well some, let's say, challenges, and one for sure is the acoustical behavior of these actuators its own, but as well, which we'll see later, the control strategy, the different controls has a huge influence on the behavior of the system. So for sure you can have all these, let's say, features, but as well during the development you have consider all these aspects to develop a very good control strategy. So as said, I focus on the part of NVH or acoustic of a system. Typically, for sure, we have our requirements, so we have customer requirements, own requirements, or just, let's say, some kind of given tasks. And then, as said, if we're talking about different products, different control strategy, it's important to include all different aspects. So for sure, we have our simulation group, we have the design, which is relevant, but as well the controls and algorithm, the system engineering, but as well operations. If it's come to the production, it's an important point because it's not only in development as well. When we just saying, okay, we develop a motor or e-motor, then typically we start with some kind of nominal design, but in reality, in production, it becomes to variations, and this has to be considered during development, that the development is stable enough or robust enough to as well overcome these variations in the production. And then that's our, let's say, mission, that we have some kind of best-in-class acoustic performance for our products, but nevertheless we have to look that we have some kind of flawless production launches, that as well the margin is still there, because typically you can say, okay, I want to have the best acoustic, so I put everything in what is possible, but in the end as well we have to see that our products has to be cost competitive, so we need as well to look in the margin. And as said, if we're talking about acoustic as well, this is some kind of comfort aspect, but as well some kind of reaction in the production or customer complaint on the field. With all that said, we have our so-called WIP strategy, which combines all the different aspects and different functions regarding the acoustical development. And just a, let's say, rough overview about what we're doing there and what is our, let's say, what is the idea behind is, for sure, we want to integrate the product into a system. And if we're talking about acoustics, typically you have this kind of noise source, where the noise is coming from. So that's the point where you can work to reduce the noise source. Then as well you have the transfer path through the system. Typically we different between structural borne noise, so going through the structure, and airborne noise. And as well you have the driver or the user of a system, so with his ears and this subjective perception. Typically, that's something we don't work on, so we're not working on ears or giving you something in your head that you didn't hear anything anymore. Yeah, so no, not our task. So where we're working on is the rest, so working on the noise transfer path and the noise source. So that's a typically, let's say, acoustical explanation of a system. And when you combine it with the modern V development approach, you see typically you have the requirements flow down on the left side and the test or the validation on the right side from a V. And if we now compare it to the, let's say, noise behavior, then you can write this a little bit. Yeah, so as I said here, you can as well write it here, and that means in the end, come to it here. So when we have a system and a subsystem, so between that in an acoustical explanation or equation, there is the noise transfer path between the subsystem and the system. So how the noise is transferred from the subsystem into the system, and that means for the requirements flow down, for sure you can define limits on a system, on a vehicle, whatever, and then by estimating the noise transfer path, you can break down the limits to the subsystem. So knowing, okay, if I have in a vehicle limit, whatever a noise spectrum over frequency, which is allowed, and I can see, okay, I have my noise transfer path. That means in the end, I need this and this noise pattern in my subsystem, and then as well you can break it down to further subsystem components and so on. And at the other hand, for sure, we have the testing, so you're testing on subsystem, on component level, and then by having the noise transfer, maybe virtual, we can as well in the first stage estimate what will be the output on a higher level, or even in vehicle. So that's nothing specific, but yeah, as we're talking about acoustic here, you see as well the very important part is not only the source of the noise, it's as well the noise transfer path and how the system reacts on the source. So yeah, by that said, so you have the customer as said and the people who listen to it. At the other hand, you have the noise propagation and for sure the noise excitation. For the noise propagation, yeah, as well this is not only in one direction, as well you have some kind of subsystem. Yeah, here's just a representation, different subsystems which can interact between each other. And for sure then on a level below you have the forces, which are the physical behavior of the noise, which in the end excites the system. And they are typically driven by some design parameters, but as well by process parameters and process capabilities during the production. So when we're talking about electrical engines, a lot of noise issues coming from some kind of imbalance things, from uneven distributions, from let's say misalignments, which are on a nominal design typically okay, but as we're coming then to a real product, for sure there is always a small deviation, which is typically in some kind of tolerances, but that's driving then the noise behavior. For the noise propagation, as a supplier or tier one, for sure we have not everything in our hand. So yeah, that's shown here. So we have the noise source for sure, that are our products, so we can work on it. We have as well the noise transfer through our parts. So here is shown for a steering gear. Yeah, as well if this motor is somewhere sitting here, yeah, the noise is somewhere transferred, if it's structural noise, through the steering gear to the housing, to the chassis components, into the subframe, and then somewhat in the subframe through driver's ear. So that's the noise path. That means, yeah, as we are only responsible for that part, we need the support of our customers or of the OEs to get at least information about these paths or doing some optimizations here. So that's not in our hand, but typically we do this together then with our customers. And as well, here's just an example showing what we're typically doing is we're doing some kind of TPA to measure the noise or the transfer part of a vehicle, and as well we can see here's just a sample, a very high and with a low amplification, and that well as means just by that we see differences in different vehicles. That means in some you can have, let's say, a louder source, but due to the transfer to the system, to the damping, it's not coming to the driver's ear. That means in the end, in the other way around, if we have a very bad transfer path to the system, we need to add more measures or even add doing more in the development process. And that's for sure leading to higher costs. And that means in the end, it's some kind of a decision to say, okay, I can do very simple things in my transfer path, in the chassis, which maybe is costing not that much, and then I can reduce the cost at the actuators. For sure, that's always a discussion which has to be made together with our customers, and it's not always that simple as shown here. Coming back to our, let's say, requirements flow down, as said, we have the testing side, and here we as well not only having a physical test, we as well have some kind of virtual tests or simulation which we use. And you see the cascading down here from the, let's say, the different component. For sure, if we are in the vehicle, as it's not in our responsibility, we don't have something virtual. For sure, if we have a vehicle on hand, we can do a physical test. Then breaking it down more to a subsystem, system components, we have our simulations on hand, which we use as well for testing. And if it's really coming to the, let's say, the physics and the inner mechanics in the e-motor, so the source forces, then for sure that's somewhat which is very, very complex to measure. To have some kind of blocked forces, and so we will see that's what measuring, but to measure the inner forces, the magnetic field, for sure that's possible, but nothing we typically do. So there we use our simulation capabilities to know, okay, that's then the behavior there are differences, and we then just measure the output, let's say, on a system level. And as well as said, not only the component is relevant, as well the connection between the things, and for sure we have here some kind of virtual tests or virtual estimation of structures and transfer paths, but as well there are methods to measure it physically. I mean, why we're doing all this virtual testing, for sure, is to save money, as well to have sometimes more or a faster development process, and as said, to have a deeper understanding of the mechanisms which are ongoing. And for sure, if we're talking about the development process and even ever shorter coming development processes, it's an issue that sometimes you don't have the hardware in hand very early. So you have a design on a paper, you have a CAD model, but you don't have the part available. Even you don't have a vehicle, don't have a real vehicle representation. So that means we have to do some kind of virtual estimations to see, okay, our product is capable and our product is capable in this vehicle. Because as said, the transfer path of the vehicles plays an important role, and if I don't have it, sometimes I have only a virtual representation of the vehicle, then we need our simulation techniques to mitigate the behavior in the vehicle. As said, from the test side, we have tests on different levels. So we're testing on component level, subsystem level, but nevertheless still as well for acoustical and drive behaviors is then in the end done on vehicle level in the vehicle. So we're driving still in Sweden or somewhere in the north of Europe on ice plates, as well in AP in America. So still the driving on ice in every winter session, summer sessions in desert areas, in very hot areas. So there's still these tests ongoing. As said before, there is a lot of virtual still there, but the final validation is always done in the vehicle in the end. And if we're talking about comfort aspects, NVH and acoustics, typically there are requirements as defined, so some limits, but in the end, if it sounds bad, it sounds bad. So you can have limits as much as you have. If you're sitting in a vehicle and it's not sounding what you like or what is expected, then you have to work on it. So that's then the reality beside all the nice processes I've shown here. Nevertheless, we have as well developed our own, let's say, measurement device for these vehicle measurements for steering. So that's some kind of, let's say, measurement device to measure the steering position or the steering velocity of the steering wheel. Yeah, for sure, this data typically are on the CAN bus. You can get them from the bus, and then knowing the steering angle. But yeah, if it's just a vehicle, you don't want to plug something in. You just can use this smart sensor and measure the steering wheel velocity. And that's for why we are doing this. So that's then shown here in this small plot. Yeah, not that nice one because it's in a video, but that we are doing to get some kind of order information. So if we have an electrical motor, which is the driver in the background of the steering gear, I need the information about the speed to do a proper order analysis. And with an order analysis, I get the breakdown to a motor order or to orders. Not all is motor orders, there are other in, but by seeing the different orders, I can estimate, okay, this is coming from the, let's say, magnetic field or so on. So that's typically when we're talking about e-motor noises, we're focusing a lot of order, so there is not all order-related noise, so speed-dependent noises, there as well are constant frequencies in, like if you hit an eigenfrequency or something like this. But typically in motor noise, there's a lot of order, so speed-related noises in. And by getting this information, you can easily can give some insight where it's coming from. So, yeah, from the vehicle down to the component. So I switched over the system test and so on. That's here just a representation of some very easy and very simple test which we're doing to get some information about the motor noise behavior. So that's a called free-free test. So in free-free condition, for sure in real world it's not really free, so you still have to hang the motor here on some bungees because you can't let them just fly in the room. But typically that's let's say the easiest condition you can do. Don't touch a motor there and then purely measure the motor. That's what we're doing here with different speeds, different loads. So as well, that's important, especially for some of these designs. You have to consider if you have, if you not have only axial load, you have as well radial load. Then you have to as well to build some device where you can apply the real load conditions. But in this case, yeah, we have only or mainly axial load, so that's why we have only axial loads here. And we drive the motor with no controller, nothing, so it's just driven by a backing EMF. So that's then as well a test where we just see the purely behavior of the motor. So no control, no nothing. And as well, here's just an example where we see different patterns, and as well there we can estimate what happened here. So as we can see here, under higher loads, the good and the bad motor are more or less the same, but at lower loads, one motor has higher excitations, and that's an indication that there's something with the bearing not okay, and so on. For sure as well, you can do some order cuts, looking into the order, so that's just a picture I just grabbed to see which are the main orders from your electrical field, and doing some optimization here. That's the, let's say, simplest representation we use. And at the other hand, we have very complex measurement devices where we have so-called 6 degree of freedom rig, where we then measure the forces or the blocked forces in the end. For sure, we as well measure torque, vibration, and so on. But with 4 force cells, we are able to measure in all 3 dimensions, and as well the rotational dimensions, the forces. The system is fully controlled via a hill, so we have the full controller in loop, so we can as well see what is the controller doing and what is the controller influence, and doing some work on the controller optimization. So that's then the other, let's say, more complex test on SIST or on EPP level. And as shown before, we have then between this purely component testing as well as some subsystem and system testing where we integrate the things into some structures. As well, this is just the short overview about our simulation approach, where we have the software or the EPP model, so our electronic power pack with the controller. We have the electromagnetic simulation and as well the integration in the mechanical structure. And as seen before, let's hear some output here. So we have here our, let's say, order spectrum, so in counterclockwise and clockwise direction from the measurement results. So that's in the end the, let's say, the frequency over the motor speed. So you see this lines which are representing orders and horizontal lines which represent a constant frequency. And as well, you see the picture of the output from our simulation, it looking somewhat the same. So that's at least then our simulation approach. And here it's much simpler to do some kind of variation studies on the controller loops as well on the EM simulation than in real world, because there you need always hardware or having some kind of tuning and some test, which is typically in the software much faster than in the real life. Yeah, that's just some issues we're facing on. So misalignment magnets, motor design for sure plays an important role. As we have typically a redundant system, we have some kind of dual lane concept motors, so we have to ensure that we have the phases aligned, and for sure the flux variation or the electrical field variation driven by multiple parameters have a huge influence. In general, I think we can summarize, we have these kind of different sources, so the mechanical noises, which is coming as well from the bearings in the motor, rotor imbalances, misalignments. We have then the aerodynamic noises, air turbulences. Typically for our small actuator motors, we don't have fans, so that's not an issue, but as well, the rotor itself is an aerodynamic part. If it's turning fast, it could get some noise. Not that much in the actuators typically we're facing, so it's more than the electromagnetic noise coming from the magnetic field, from the ear gaps, unequal air gaps, misalignment, slot misalignment, screwing issues, and so on. But nevertheless, coming to the end, not only the hardware itself, not only the physics, the magnetics, or in the motor has an influence as well. The controller and how you design a controller is an important part for the motor noise. That's just a, let's say, artificial representation of a very simple motor control. Yeah, there's much more, but let's start with a simple one here. To see what we have. Yeah, for sure the controller itself, so the control strategy, gain, but as well as important is the time constants you're using. If you have a more complex controller loops with different controllers, as well how different time constants are synchronized, how your synchronize is working is a very important point for noise. So if you're doing wrong things there, you can have a lot of issues just by if the synchronization is not working proper. And for sure, the motor speed always plays a role. So if we have our actuators, we have to have a given performance we want to fulfill. But as well, the question is the motor in the upper end running, so that more, let's say, oversized or undersized plays a role for the acoustical behavior. But as well, you have some sensors. Typically, you have some input signals for your control loop. Here, let's say some outer sensors, which are not in the inner control loop, from an outer control loop, like the vehicle speed or something. And as well, here the noise on the signals plays a role, because if your controller is always working and controlling out something, it typically generates more noise than when it's running smooth. And as well said, the discretization is always very critical in the combination with the time constants in your controller approach, as well the sampling rate, which is somewhat related to this and the discretization. And you typically have some kind of lookup tables or something in your input fast as well. Here the numbers of nodes, the interpolation method plays an important role. Also smoothing out factors as well. Here we're coming to the point, if this is not proper working, you always have to change something in the control, so you have not a smooth running of the system, and that's leading to some noise. And as well, typically in a control loop, you have as well your sensor, so the feedback sensor, and here you have the same thing, so the noise discretization and sampling rate plays an important role. So meaning, just for an example here, not going too much into details, if you do a motor design, on one hand, that's relevant, but if you do the control design or design your controller for a motor, that's as well very important. And as said in the beginning, as we have a more complex system with different actuators working together, this aspect is really the, let's say, the key challenge to work on, because then the controller representation will not look like this simple diagram here. But let's say the issues and the risks are the same, but in a more complex system to solve. So coming to an end, what have we seen today? What have I shown? We have our system development, so-called. It's somewhat in an, let's say, ASPICE process embedded. We have these flow down, requirements flow down. We have the testing method or testing validation, which is built in our development process. Not only developing one single actuator, we're developing a full vehicle motion controller with different actuators, and having then the vehicle integration process to implement that from the component to the system into the vehicle. And at the end, as shown, for all this, some kind of very enhanced control strategy is needed as well for acoustical optimization and comfort optimization. So thank you very much for your time, and hopefully you have some questions.
So good morning then.
Alexander Siefert from Simosurf. Thank you for the very interesting presentation. I have two questions. The first one, you talked about comfort. Comfort is very difficult because it's a kind of perception. And we have two parts in that perception. The one is the customers, but also the brands have some perception, especially for typical engines. Each OEM has his desire how the engine should, what should be the engine sound. Do you see something similar here? And the second?
Make the second.
And the second question would be, you mentioned about the virtual simulation, virtual twins. On structural, when we look on crash testing, no car is produced before you have not fulfilled all crashes virtually. Acoustics is much more difficult. How do you see that in the future?
So with the differentiation, yes, comfort is always some kind of unique perception what you have, and typically, for a drivetrain, you have this kind of unique pattern of an engine. Here as well, for our products, as not the drivetrain product, so that's maybe something different, but for the actuators, typically there are two different, let's say, overall aspects you have to consider. First, there are actuators where you want to hear something, like a parking brake. If you're switching the small little button in your vehicle, then you want to have some kind of feedback that there's something working, because it has to stop your car and you want to leave, and you want to know not only a sign there, you want to hear something. So a parking brake typically is designed with some kind of feedback sound. That means it should not sound whatever wrong, so it sounds somewhat to the action you're doing. So it's typically having some kind of different different frequencies, that it's like, so it's showing something, there's something clamping. Yeah, the sound is designed to show it's something clamping. It's not that complicated because it's still the function which is doing, so we don't have to do it artificial, and the function typically is a thing which drive it. And then you have other systems like a steering system. Yeah, everybody knows, okay, I have a servo drive or something, yeah, so people knowing there is some support, but that not expecting when they're steering that they hear something. So there you need motors which are very quiet. And yeah, that are let's say the general different aspects we have to consider for different actuators. So the ones which you want to hear and the others not. But as shown, we typically try to use the same product for both, and that makes things complicated because yeah, if we do develop things, for sure you can always overdevelop and say I have a very quiet motor, very perfect, and just making artificial noise that will always work. But then we come to the point of costs. Yeah, and that's a little bit the player here to have more or less the same thing with different noise pattern, and that makes things complicated. As well, there are, let's say, regarding comfort, there are for sure different aspects from our OEs. So that's especially about not more about the noise itself, it's more really, if we're talking about comfort, it's about the feeling. So for sure as well, if we're talking about noise, vibration, and harshness, it's as well about the feeling, how is the torque ripple, how direct is your steer feel, what is the brake pedal force you pressing, and all this stuff, how is the reaction time. That's then as well different from OE to EOE, and we have to adapt our control strategy regarding these let's say unique requirements. To the simulation, yes, it's complicated. As said, if we really coming from the, let's say, from the bottom, when we're talking about the physics, the magnetic forces, I think the simulation are well established. So there is a lot of, let's say, physics behind. If it becoming to a more complex system, it's still physics, but the physics getting complex because you have so many variables you have to consider. You have to at least validate or measure that let's say, you have to do much more estimations. And that means in the end, if we're doing a, let's say, full system representation of our system, the occurrence goes down. That's for sure. And if we're then coming to the vehicle, as said, that's not in our hands. We really have to rely on the OEs and their capabilities to know what is their chassis acting like. And there are, as well differences available, so people knowing more. And it could always happen, there was a design done, it was proved, it was all whatever simulated, but then there is a, let's say, small change because there has to be adding a rib somewhere due to crash reasons or whatever. And let's say, the transfer behavior totally changed. So that's always happening.
Yeah, good morning, and thanks a lot for this presentation. You have introduced that you have some software and hardware for in your testing. Let me see. In your measurement and testing, and I think a very interesting tool is this VMC vehicle motion control and the softwares. Oh, I have written it down where it is. So the software so far, which is hardware and software, software and hardware with a sensor in combination with a NVH ear Bluetooth microphone. Is this a software we can purchase from you, or is this your development which is on the staying on your side? So question number one, and common question number two is, do you see differences between the ICE vehicles and e-vehicles on the demand for noise reduction? So when I have not the combustion engine, which is covering a lot of transmission noises and so on, is there a new field of investigation which is now opening for us?
So to the first question about the SOFA tool, you are not the first one who's asking, so but the answer is no, because we are not able to have some good of software support and all this stuff, so that's why we decide, yeah, we have as an idea to have as in the company as well selling software, but at the moment not on let's say on this level. So at the moment not. Maybe it will come because as I said, you're not the first one who asking for that. To the second question, yes, for sure. The electrical vehicle, first of all, they reducing the background noise. Yeah, that's the very simple thing you can imagine. Yeah, if you have not a combustion engine in the background noise is less. And if we're talking about low-speed applications like parking maneuvers and so forth, for sure that plays an important role. That's something we have to consider. So making even quieter actuators than for a combustion engine. But there are two other aspects. The first aspect is that the battery itself and let's say the weight of the battery and how it's distributed in the vehicle have an influence on the chassis itself, and that means typically in electrical vehicles the chassis or subframes have changed due to combustion engine. And as said, as we as well talking not only about the source as well as the transfer fast, as well that plays a role, that typically that we have differences in between the chassis or the subframe between electrical vehicle and combustion engine vehicle, and that means different transfer fast, different behavior of the transfer fast. And the third, not to forgiven aspect is a little bit if we have this kind of let's say secondary damping, secondary noise isolation in a vehicle. Typically in former times, yeah, when you have a combustion engine, it has some kind of noise which couldn't be reduced to a limit of 0. So what typically OEs did, they implement some kind of damping material, damping walls in the doors, somewhere damping material here and there. So if now the engine is quiet more or less, it's no longer used or has to be used. So they reduce it due to cost. So the damping indoors and so all this is going back. That means as well for our actuators it becomes more complicated because we have less background noise and we have less damping in the structure of the vehicle. And that for sure makes the things more complicated and in the end more cost intensive. So we have to do more, have to have better, let's say, processes with smaller tolerances, which in the end driving the cost for our products. Yes.
Okay, then thank you very much. We come now from a lot about motors and components, and now we come to